Good afternoon to all. Today we are discuss one of the GET topic LC oscillator from analog circuit. This topic is delivered under the scheme of AICTE PRERANA. Myself and JOTHIPPRIYA, Assistant Professor, Department of Electrical and Electronics Engineering, Erode Sengunthar Engineering College, Perundurai, Tamil Nadu. Now let us see the topic LC oscillator. Before enter the topic, first we know about what is an oscillator and its type and what is the condition for oscillation. Now first see the what is an oscillator. An oscillator is an electronic circuit which produces an AC output without any input. In other words, an oscillator is an amplifier which uses positive feedback. An oscillator is an amplifier which uses positive feedback and it generates an output waveform at desired frequency without any external input signal. Now, let us see the types of oscillator. The oscillator can be mainly classified based on their waveform output production into two types. One is sinusoidal oscillator and another one is non-sinusoidal oscillator or relaxation oscillator. The example for sinusoidal oscillators are LC oscillator and RC phase shift oscillator. The examples for non-sinusoidal oscillators are sawtooth wave generator and UJT relaxation oscillator. An oscillator produces oscillation. It requires oscillatory circuit, amplifier circuit, and feedback network. Oscillatory circuit consists of inductance and capacitance to produce oscillation. Amplifier circuit has FET amplifier or BJT amplifier or operation amplifier, that is any one type of amplifier. It gives additional energy to compensate the loss produced by oscillatory circuit. The feedback circuit fed back output to input. Here we are using positive feedback. That means the output signal is added to input signal. Now let us see the condition for oscillation. An amplifier circuit acts as an oscillator. It satisfies two conditions. The first condition is the total phase shift around the loop is 0 degree or 360 degree. The second condition is the magnitude of product of the open loop gain of the amplifier A and feedback factor beta is unity. That is, modulus of A beta is 1. The condition for oscillation is the total phase shift is equal to 0 degree or 360 degree and modulus of A beta equal to 1. Now let us see the today's topic LC oscillator. LC oscillator consists of L and C elements to produce oscillation. So it is called as LC oscillator. It is also known as resonant circuit oscillator or tank circuit oscillator or tuned circuit oscillator. This oscillator produces output frequency ranging from 1 MHz to 500 MHz. So it is also called as RF oscillator. The LC oscillator consists of one amplifier circuit and one tuned circuit. The LC oscillator mainly used in transmitter and receiver circuits. Now let us see the tank circuit operation of LC oscillator. In the LC oscillator, the tank circuit consists of inductance and capacitance which are connected in parallel. Now let us assume the capacitor is initially charged from the DC source with the polarity as upper plate of the capacitor is positive and lower plate of the capacitor is negative. When the capacitor is fully charged, the electrostatic energy is stored in capacitor. But capacitor is connected parallel to the inductor. So the capacitor is discharged through the inductor with one direction. We are assuming the direction is in clockwise. Now, due to the flow of current, the magnetic field is set up around the inductor. This causes magnetic energy is stored in the inductor. When the capacitor is fully discharged, total electrostatic energy is stored as magnetic energy in inductor. Now the magnetic field of the inductor L start collapsing. As per the Lenz's law, the capacitor starts charging with the opposite polarity, making lower part is positive and upper part is negative. After some time later, the capacitor is fully charged in opposite polarity of its initial polarity. Now the magnetic energy is converted back to electrostatic energy. Now the capacitor is again discharging through the inductor in opposite direction, that is anti-clockwise direction. So the electrostatic energy is again converted into magnetic energy. Now the magnetic field is again collapsed. So the capacitor is again charging the opposite polarity. So every time the energy is transferred from C to L and L to C, this causes losses increasing. The amplitude of the oscillating current is decreasing. But an LC oscillator having a transistor amplifier. This transistor amplifier gives the energy to compensate the loss produced by the LC circuit. So we get sustained oscillation. In LC oscillator, frequency of the oscillation depends upon the L and C value, that is inductor and capacitance value. So in LC oscillator, the frequency of the oscillation F is equal to 1 divided by root of L into C hertz. Now let us see the analysis of LC oscillator. Figure shows the general form of LC oscillator and its equivalent circuit. The general form of LC oscillator circuit consists of amplifier circuit and feedback circuit. The amplifier circuit may be FET amplifier or BJT amplifier or operational amplifier. The feedback circuit consists of reactive element Z1, Z2 and Z3. And the feedback circuit determines the frequency of the oscillation. In the figure, the output terminal is 2 and 3 and the input terminal are 1 and 2. So, Z1 and the input resistance HIE are in parallel condition. Now the equivalent impedance of the LC oscillator Z dash, that so 1 by Z dash equal to 1 divided by Z1 plus 1 divided by HIE. Now taking common denominator for these two terms, we get 1 divided by Z1 equal to HIE plus Z1 divided by Z1 plus HIE. Now rearranging this equation, we get equivalent impedance Z dash equal to Z1 into HIE divided by Z1 plus HIE. Now the load impedance ZL between the output terminal 2 and 3 is the equivalent impedance of Z2. The load impedance ZL between the output terminal 2 and 3 is the equivalent impedance of Z2, is in parallel with the series combination of Z1 and Z3. Therefore, 1 divided by ZL equal to 1 divided by Z2 plus 1 divided by Z dash plus Z3. Now substituting Z dash value, we get 1 divided by ZL equal to 1 divided by Z2 plus 1 divided by Z1 into HIE. This term is divided by Z1 plus HIE plus Z3. Now, we are taking common denominator in the second term and simplifying the second term. We get the second term is Z1 plus HIE divided by Z1 into HIE plus Z1 into Z3 plus HIE into Z3. Now 1 divided by ZL is equal to 1 divided by Z2 plus Z1 plus HIE divided by Z1 into HIE plus Z1 Z3 plus HIE into Z3. In the second term, HIE is common for Z1 and Z3. So taking HIE outside, we get 1 divided by Z2 plus Z1 plus HIE divided by HIE into Z1 plus Z3 plus Z1 into Z3. Now taking common denominator for first and second term, we get HIE into Z1 plus Z3 plus Z1 into Z3 plus Z2 into Z1 plus HIE. The whole term is divided by HIE. The term is multiplied into Z1 plus Z3 plus Z1 into Z3. The whole term is multiplied by Z2. Now rearranging the equation, we get 1 divided by ZL equal to Z1 plus Z2 plus Z3. This term is multiplied by HIE plus Z1 into Z2 plus Z1 into Z3. That whole term is divided by HIE multiplied by Z1 plus Z3 plus Z1 into Z3. The whole term is multiplied by Z2. Now taking reciprocal, we get total impedance ZL. The value of ZL equal to HIE into Z1 plus Z3 plus Z1 into Z3. The whole term is multiplied by Z2. The whole term is divided by Z1 plus Z2 plus Z3. This term is multiplied by HIE plus Z1 into Z2 plus Z1 into Z3. Now, we get voltage gain without feedback AV equal to minus HIE into ZL divided by HIE. And the feedback fraction beta equal to VFB divided by V0. Here VFB equal to Z dash divided by Z dash plus Z3 into V0. Now substituting Z dash value, we get VFB equal to Z1 parallel HIE divided by Z1 parallel HIE plus Z3. The whole term is multiplied into V0. Now simplifying and rearranging this equation, we get beta equal to Z1 into HIE divided by HIE into Z1 plus Z3 plus Z1 into Z3. Now let us see the condition for oscillation. Condition for oscillation equal to AV into beta equal to 1. That is open loop gain and feedback factor product is equal to 1. That is AV into beta equal to 1. Now substituting AV and beta value, we get minus HFE into ZL divided by HIE into Z1 into HIE. The term is divided by HIE into Z1 plus Z3 plus Z1 into Z3, that is equated to 1. Now multiplying these two terms and rearranging and simplifying, we get HFE into Z1 plus Z2 plus Z3 plus Z1 into Z2 plus Z1 into Z3 equal to minus HFE Z1 Z2. Now shifting the minus HFE Z1 Z2 value from right side to left side, we get HFE into Z1 plus Z2 plus Z3 plus Z1 into Z2. This term is multiplied by 1 plus HFE plus Z1 into Z3 equal to 0. This is the final general equation for LC oscillator for the condition of oscillation. The LC oscillator can be classified based on their feedback circuit, Hartley oscillator, Colpitts oscillator, and Clapp oscillator. Now let us see Hartley oscillator. Hartley oscillator consists of one amplifier circuit and one feedback circuit. The amplifier circuit is normal common emitter BJT amplifier. The BJT amplifier gives 180-degree output between their input and output. 180-degree phase shift between their input and output always. The feedback circuit consists of two inductor and one capacitor. The feedback circuit, two inductor is connected parallel to capacitor. In the feedback circuit, the upper terminal is denoted 1 and the lower terminal is denoted 2. The center terminal is denoted 3. At any time, the upper terminal 1 is positive polarity with respect to 3 and number 2 is negative polarity with respect to 3. So, at any time, phase shift between the feedback circuit from 1 and 2 is 180 degree. So, total phase shift of the Hartley oscillator is 360 degree. Now we are adjusting AB and beta value that is equal to 1. This circuit is act as oscillator. Now let us see the operation of Hartley oscillator. When switch on the supply, the capacitor is charged. When the capacitor is fully charged, it starts to discharge through inductor coil L1 and L2. It sets up the oscillation of frequency. The output voltage of the amplifier appear across the L2 and feedback voltage across L1. Hence, the L1 and L2 forms or act as a potential divider. The terminal 3, that is center terminal of the feedback circuit, is earth potential. The terminal 1 is positive potential and terminal 2 is negative potential. So phase shift between 1 and 2 in the feedback circuit is 180 degree. Now let us see the analysis of Hartley oscillator. First, we see the frequency of oscillation of Hartley oscillator. In Hartley oscillator, Z1 and Z2 are inductive reactance, Z3 is a capacitive reactance. So the value of Z1 equal to j omega L1 and Z2 equal to j omega L2 and Z3 equal to 1 divided by j omega C, that's equal to minus j divided by omega C. The general equation for the oscillator, that is LC oscillator, is Z1 plus Z2 plus Z3. This term is multiplied by HIE plus Z1 into Z2. This term is multiplied by 1 plus HFE plus Z1 into Z3 equal to 0. Now substituting Z1 and Z2 and Z3 value, we get HIE into J omega L1 plus J omega L2 plus 1 divided by J omega C plus J omega L1 into J omega L2. This term is multiplied by 1 plus HFE plus J omega L1 into 1 divided by J omega C equal to 0. Now simplifying this equation, we get HIE J omega into 1 L1 plus L2 minus 1 divided by omega C minus of omega square L1 L2 minus omega square L1 L2 HFE plus L1 divided by C equal to 0. Now we are giving this is equation number 2. The general equation is equation number 1. To determine the frequency of oscillation, the imaginary part of the equation number 2 is equal to 0. So, WHIE, that is omega HIE, this term is multiplied by L1 plus L2 minus 1 divided by omega C equal to 0. The value of WHIE equal to 0. So, this equation is now modified into L1 plus L2 minus 1 divided by omega square C equal to 0. Now simplifying this equation, that is shifting the minus value from left side to right side, we get L1 plus L2 equal to 1 divided by omega square C. From the above equation, we get omega square equal to 1 divided by L1 plus L2 into C. This term is multiplied by C. That is omega square equal to 1 divided by C into L1 plus L2. Now substituting omega equal to 2 pi f, we get 2 pi f the whole square equal to 1 divided by L1 plus L2. This term is multiplied by C. Now simplifying this equation, we get f squared equal to 1 divided by 2 pi into L1 plus L2. This term is multiplied into C. We need frequency of oscillation. So taking square root, we get frequency of oscillation of Hartley oscillator. F is equal to 1 divided by 2 pi into square root of L1 plus L2. This term is multiplied into C, that is capacitance. Here L equivalent equal to L1 plus L2. Now replacing L1 plus L2 is equal to L equivalent, we get frequency of the oscillator F equal to 1 divided by 2 pi into square root of L equivalent into C. Now let us see the condition for oscillation of Hartley oscillator. We get condition for oscillation of Hartley oscillator. The real part of the equation number 2 is equal to 0. The real part of equation number 2 is minus omega squared L1 into L2 minus omega squared L1 L2 HFE plus L1 divided by C equal to 0. In this equation, omega squared L1 L2 is common for first two terms. So taking outside, we get omega squared L1 L2. This term is multiplied by 1 plus HFE minus L1 divided by C equal to 0. Now shifting the minus L1 divided by C value from left side to right side, we get L1 divided by C equal to omega squared L1 L2. This term is multiplied 1 plus HFE. Now substituting omega squared value, The omega squared value is getting from equation number 3. That is omega squared equal to 1 divided by L1 plus L2. This term is multiplied into C. So substituting this value in the equation L1 divided by C equal to 1 divided by L1 plus L2 into C. This term is multiplied into L1 into L2. This term is multiplied into 1 plus HFE. Now simplifying and rearranging this equation, we get L1 equal to L1 into L2 divided by L1 plus L2. This term is multiplied into 1 plus HFE. Now again simplifying this equation, we get L1 plus L2 divided by L2 equal to 1 plus HFE. Now separating and simplifying this equation, we get 1 plus L1 divided by L2 equal to 1 plus HFE. Now cancelling the value of 1, we get HFE equal to L1 divided by L2, that's equal to beta. This is the condition for oscillation. But in practical, the two inductor is wind same core. So it exists mutual inductance between them. We are denoting the value of mutual inductance is M. So considering mutual inductance in Hartley oscillator, the L equivalent value is equal to L1 plus L2 plus 2M. Considering mutual inductance, the condition for oscillation HFE or beta value is equal to L1 plus M divided by L2 plus M, because Z1 equal to J omega L1 plus J omega M and Z2 equal to J omega L2 plus J omega M. Now let us see the another type of LC oscillator, Colpitts oscillator. Colpitts oscillator consists of one amplifier circuit and one feedback circuit. This amplifier circuit is common emitter amplifier. This common emitter amplifier provides 180-degree phase shift between their input and output. The Hartley oscillator consists one feedback circuit. That feedback circuit consists two capacitor and one inductor. This two capacitor is connected parallel to the inductor. This feedback circuit gives 180-degree phase shift. So total phase shift of the oscillator is 360-degree. In the feedback circuit, the upper terminal is denoted 1 and lower terminal is denoted 2, center terminal is denoted 3. At any time, the center terminal is connected to ground potential. So, at any time, the upper terminal 1 is positive with respect to 3 and lower terminal 2 is negative with respect to 3. So, at any time, the phase shift between the feedback terminal 1 and 2 is 180-degree. So we are switching on the supply. The capacitor is charged. When capacitor is fully charged, it's discharged through the inductor. It produced damping oscillation. The amplifier compensates the loss produced in the LC circuit, so we are getting sustained oscillation. Now let us see the analysis of Colpitts oscillator. First, we are see the frequency of oscillation of Colpitts oscillator. In Colpitts oscillator, Z1 and Z2 is a capacitive reactance, whereas in Hartley oscillator, Z1 and Z3 is inductive reactance. Here, Z1 and Z2 are capacitive reactance, Z3 is inductive reactance. So value of Z1 is equal to 1 divided by J omega C1 and Z2 equal to 1 divided by J omega C2 and Z3 equal to J omega L. And the general equation for LC oscillator is Z1 plus Z2 plus Z3. This term is multiplied into HIE plus Z1 into Z2. This term is multiplied into 1 plus HFE plus Z1 into Z3 equal to 0. This is the general equation for LC oscillator. Now substituting Z1, Z2, Z3 value, we get HIE into 1 divided by j omega C1 plus 1 divided by j omega C2 plus j omega L plus 1 divided by j omega C1 into 1 divided by j omega C2. This term is multiplied by 1 plus HFE plus 1 divided by j omega C1 into j omega L is equal to 0. Now rearranging and simplifying this equation, we get j into HIE. This term is multiplied by minus 1 divided by omega C1 minus 1 divided by omega C2 plus omega L minus of HFE divided by omega squared C1 into C2 minus 1 divided by omega squared C1 C2 plus L divided by C1 equal to 0. Now we are denoted this equation is number 2. The general equation of oscillator is denoted number 1. We are getting frequency for oscillation. The equation number 2 imaginary part is equal to 0. The equation number 2 imaginary part is HIE into 1 divided by minus omega C1 minus 1 divided by omega C2 plus omega L, that is equal to 0. We are getting frequency for oscillation. So now that is minus 1 divided by omega C1 minus 1 divided by omega C2 plus omega L equal to 0. Now rearranging this equation, we get omega L equal to 1 divided by omega C1 plus 1 divided by omega C2. Again rearranging and taking common term outside, we are getting omega square L equal to 1 divided by C1 plus 1 divided by C2. Replacing 1 divided by C1 plus 1 divided by C2 equal to 1 divided by C equivalent. So we are getting omega square L equal to 1 divided by C equivalent. From the above equation, omega equal to 1 divided by square root of C equivalent into L. Here C equivalent equal to 1 divided by C1 plus 1 divided by C2. 1 divided by C equivalent equal to. So frequency of the oscillation F, now we are replacing omega equal to 2 pi F. So the equation is modified 2 pi F equal to 1 divided by square root of C equivalent into L. From the above equation, we are getting frequency F equal to 1 divided by 2 pi square root of C equivalent into L. Here the C 1 divided by C equivalent value equal to 1 divided by C1 plus 1 divided by C2. Now let us see the condition for oscillation of Colpitts oscillator. We are getting condition for oscillation of Colpitts oscillator. The equation number 2 real part is equal to 0. The real part of equation number 2 is minus HFC divided by omega squared C1 C2 minus 1 divided by omega squared C1 into C2 plus L divided by C1, that is equal to 0. Now rearranging this equation, we get HFE plus 1 divided by omega squared C1 into C2 plus L divided by C1 equal to 0. Again we are rearranging, we get HFE plus 1 divided by omega squared C1 C2, that's equal to L divided by C1. Now cancelling the value of both sides C1, we are getting 1 divided by omega squared C2 into HFE plus 1 is equal to L. Now again rearranging the equation, we are getting HFE plus 1 divided by C2 equal to omega squared into L. Now substituting omega square L value, we are getting HFE plus 1 equal to C1 plus C2 divided by C1 into C2. The whole term is multiplied into C2. Now Separating the equation and rearranging the equation, we are getting HFE plus 1 equal to 1 plus C2 divided by C1. Now cancelling the 1 both sides, we are getting HFE equal to C2 divided by C1. This is the condition for oscillation of Colpitts oscillator. Frequency of Colpitts oscillator F is equal to 1 divided by 2 pi into square root of C equivalent into L. Condition for oscillation of the Colpitts oscillator is equal to C2 divided by C1. Now let us see the next LC oscillator, clamp oscillator. The clamp oscillator is similar to that of Colpitts oscillator, but in clamp oscillator, additional capacitor is connected in series to the inductor in the feedback circuit. Figure shows the clamp oscillator schematic diagram. In the figure, the clamp oscillator consists of one amplifier and one feedback network. The amplifier is a common emitter amplifier. It produces 180-degree phase shift between their input and output. The feedback circuit produces 180-degree phase shift between the two terminals. So total phase shift of the clamp oscillator is 360-degree. Now we are adjusting AB into beta equal to 1. This circuit acts as an oscillator. In the clamp oscillator, the feedback circuit consists of 3 capacitors and 1 inductor. The capacitor C1 and C2 is connected parallel to the series combination of inductor and capacitor C3. The upper terminal of feedback network is denoted as usual 1 and lower terminal is denoted 2, center terminal is denoted 3. The center terminal 3 is connected to ground potential. So at any time upper terminal 1 is positive with respect to 3 and lower terminal 2 is negative with respect to 3. So at any time the phase shift between the upper and lower terminal, that is 1 and 2 of the feedback network, is 180-degree. When switched on the supply, the capacitor is charged. Once the capacitor is fully charged, it's discharged through the capacitor. It discharged through the inductor. So this produces damped oscillation. The amplifier circuit compensates the losses and the total circuit gives the sustained oscillation. Now let us see the analysis of clamp oscillator. First, we are see the frequency of oscillation of clamp oscillator. The general equation for LC oscillator is Z1 plus Z2 plus Z3. The term is multiplied into HIE plus Z1 into Z2. This term is multiplied into 1 plus HFE plus Z1 into Z3 is equal to 0. We are getting frequency of oscillation. The imaginary part of the above equation is equal to 0. The imaginary part of the above equation is HIE into Z1 plus Z2 plus Z3. Now this is equal to 0. We are getting the frequency for oscillation. So this equation equal to Z1 plus Z2 plus Z3 equal to 0. The value of Z1 is 1 divided by j omega C1. The value of Z2 equal to 1 divided by j omega C2. The value of Z3 is j omega L plus 1 divided by j omega C3. Because Z1 and Z2 is capacitive reactance, Z3 is combination of inductive plus capacitive reactance. So Z1 equal to 1 divided by j omega C1, Z2 equal to 1 divided by j omega C2, Z3 equal to j omega L plus 1 divided by j omega C3. Now substituting Z1, Z2, Z3 value in the imaginary part of the general equation, we are getting minus j divided by omega C1 minus j divided by omega C2 minus j divided by omega C3 plus j omega L equal to 0. Or j omega L equal to j into 1 divided by omega C1 plus 1 divided by omega C2 plus 1 divided by omega C3. Rearranging this equation, we are getting omega square L equal to 1 plus C1 plus 1 plus C2 plus 1 plus C3. Now replacing 1 plus C1, 1 plus C2 plus 1 plus C3 equal to 1 divided by C equivalent. We are getting omega squared equal to 1 divided by L into C equivalent. Now substituting omega equal to 2 pi f, we are getting 2 pi f the whole square equal to 1 divided by L into C equivalent. From this equation, we are getting frequency of the oscillator f equal to, we are taking square root of the above equation, f equal to 1 divided by 2 pi into square root of L into C equivalent. Here the C equivalent value, 1 by C equivalent value is equal to 1 divided by C1 plus C1 divided by C2 plus 1 divided by C3. Now let us see the condition for oscillation. We are getting condition for oscillation of the clamp oscillator. The general LC oscillator equation real part is equated to 0. The general LC oscillator real part is equal to Z1 into Z2. This term is multiplied by 1 plus HFE plus Z1 into Z3 equal to 0. Rearranging this equation, we are getting Z1 into Z2. This term is multiplied into 1 plus HFE equal to minus Z1 into Z3. Again rearranging this equation, we are getting 1 plus HFE equal to minus Z3 divided by Z2. Now substituting Z3 and Z2 value, we are getting minus J. This term is multiplied by omega L minus 1 divided by J omega, 1 divided by omega C3. This term is multiplied by omega C2. This term, whole term divided by minus J. Now cancelling J value and simplify this equation, we get omega squared LC2 minus C2 divided by C3. Now substituting omega squared L value in the above equation, we get 1 plus HFE equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. This term is multiplied into C2. And this term is subtracted by C2 divided by C3. Now rearranging this equation, we get 1 plus HFE equal to C2 divided by C1 plus 1 plus C2 divided by C3 minus C2 divided by C3. Now simplifying and rearranging the above equation, we are getting HFE equal to C2 divided by C1. This is the condition for oscillation of clamp oscillator. Now let us see the LC oscillator related some workout solved problems. And the problem number 1 belongs from Hartley oscillator topic. The problem is in Hartley oscillator, L1 equal to 20 millihenry and C equal to 30 picofarad. Calculate the L2 for the frequency of oscillator is 200 kilohertz. The mutual inductance between L1 and L2 is 8 microhenry. Also find the required gain of the transistor to be used for the oscillation. Here we are giving L1 value and C value and mutual inductance value and frequency value. So solution of this problem, we know frequency of Hartley oscillator formula, F is equal to 1 divided by 2 pi square root of L equivalent into C. In general, L equivalent equal to 1 divided by 4 pi F squared, 4 pi square into F square into C. In this equation, we are substituting C value, that is 30 picofarad. We are getting L equivalent value. After substituting C value, the L equivalent value is equal to 21.11 millihenry. Now substitute this L equivalent value in the L equivalent formula. that is L equivalent equal to L1 plus L2 plus 2M. This equation, we are getting L2 value. After substituting L equivalent value from the L equivalent equation, we are getting L2 value. That value is 1.1 millihenry. Now, we are find the condition for oscillation. We know condition for oscillation formula HFE equal to L1 plus M divided by L2 plus M considering mutual inductance. So now substituting L1, L2 and M value, we are getting condition for oscillation value HFE, that is equal to 18.05. Now let's move on next sum. This sum is blanks from Colpitts oscillator topic. The sum is in Colpitts oscillator C1 equal to 0.001 microfarad, C2 equal to 0.01 microfarad and L equal to 10 microfarad. Find the frequency of oscillation, feedback factor and voltage gain. In this sum, we are giving C1 and C2 and L value. But we need a frequency of oscillation, feedback factor and voltage gain. We know the frequency of oscillation formula F naught equal to 1 divided by 2 pi square root of L into C equivalent. In this equation, first we find out C equivalent value. C formula for C equivalent equal to, here we are giving two capacitance. So C equivalent equal to C1 divided by C1 into C2 divided by C1 plus C2. Substituting in this equation C1 and C2 value, we are get C equivalent, and that value is 9.09 into 10 to the power minus 10 farad. Now substituting this C equivalent value in the frequency equation, that is F naught equal to 1 divided by 2 pi into square root of L into C equivalent, we are getting frequency of oscillation. Frequency of oscillation F naught equal to 1 divided by 2 pi into root of 10 into 10 to the power minus 6. That is the L value. That is L value, and that is multiplied into 9.09 into 10 to the power minus 10. That is the C equivalent value. Simplifying this, we get frequency of the oscillation. That value is 1.6692 megahenry. Now we are find out the voltage gain. The formula for voltage gain is C2 by C1 in Colpitts oscillator. Now substituting C2 and C1 value, we are getting voltage gain. The value of voltage gain equal to, in this problem, 10. Because C2 value is 0.01 microfarad and C1 value is 0.001 microfarad. We know condition for oscillation AV into beta equal to 1. In this equation, we know AV value. Now substituting AV value in the equation, we get feedback factor beta. The formula for feedback factor beta equal to 1 divided by AV, that is voltage gain. So substituting AV value, we get beta equal to 1 divided by 10, that's equal to 0.1. So in this problem, the feedback factor beta value is 0.1. Frequency is 1.6692 megahertz. Voltage gain is 10. Feedback factor is 0.1. Now let us see the next problem. This problem belongs from Clapp oscillator topic. The problem is calculate the inductance value to produce 734.5 kHz frequency of oscillation in Clapp oscillator having C1 equal to 0.1 microfarad, C2 equal to 1 microfarad and C3 equal to 100 microfarad. In this formula, we are giving C1, C2, C3 value, but we need inductance value. We are also giving frequency value. So we know frequency of the Clapp oscillator F equal to 1 divided by 2 pi into square root of L into C equivalent. Here C equivalent, that is 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now substituting C1, C2, C3 value, we get 1 by C equivalent value. That value is in this problem 11.01 into 10 to the power 6. Because C1 value is 0.1 microfarad, C2 value is 1 microfarad, C3 value is 100 microfarad. So taking, now substituting now taking reciprocal of 1 by C equivalent, we are getting C equivalent value. That value is 9.0826 into 10 to the power minus 8 farad. Now substituting C equivalent value in the frequency equation, we are getting inductance of this oscillator. So after substituting frequency and C equivalent value, we are getting inductance value. That value is 0.5169 microhenry. Now, let us conclude today's topic. Today we are discuss what is an oscillator and types of oscillator and condition for oscillation and what is LC oscillator and general equation for LC oscillator and types of LC oscillator and their analysis, that is Hartley oscillator, Colpitts oscillator and Clapp oscillator, and one example problem for each type of LC oscillators. Thank you.